Hello everyone, in this third lecture of inverters, we'll be learning about resonant inverters. We'll be looking at two configurations of resonant inverters. The resonant inverters are very important because they give output similar to sinusoids, and as a result, these kind of inverters are actually very useful, and these inverters have a lot of practical applications. For example, induction stoves are actually developed using these resonant inverters. Half-bridge resonant inverter is another kind of inverter which gives us near to sinusoidal voltage. So this is the circuit diagram of the inverter. As we can see, there are two switches or SCRs, T1 and T2. When T1 is switched on, the current flows in this direction. So what it does is the voltage source Vs at first charges the inductor L. After charging the inductor L, the inductor gradually charges the capacitor C, and at that phase the current flows to the resistance and goes to the negative. So while the inductor is being charged, the output voltage is rising gradually because the inductor does not allow sharp rise in output voltage, and while the inductor is getting discharged, the output voltage is falling gradually, as we can see from the graph. So once the capacitor is fully charged, the capacitor is open circuited. As a result, no current flows in this direction, and since this switch is also off, no current flows in this direction as well. As a result, we have zero current in this period. Now if we switch on and since we have zero current, our transistor 1 or the SCR1 automatically turns off through natural computation. So both the switches are turned off at this moment and the voltage is zero. Now if we switch on the transistor 2 or give a current pulse to the gate of the transistor 2, what happens is this transistor is switched on. Then what happened, the capacitor was charged with plus on the upper side and minus on the upper side. This and capacitor gets discharged. This capacitor gets discharged in this direction. This discharge of capacitor again creates a charge, again charges the inductor, this inductor, and the output voltage, since the current is now in opposite direction, the output voltage is negative. While the inductor is being charged, the output voltage is rising in the negative direction, and when the inductor is getting discharged, the output voltage is again falling in the negative direction. And once the capacitor is entirely discharged and the inductor is entirely discharged, the discharge of inductor will again charge the capacitor with plus at the bottom and minus at the top, and the capacitor will again get fully charged in the opposite direction, and it will be open circuited. And because of the presence of open circuit in here, we will get zero current. So as a result, in a resonant inverter, we are getting some kind of resonating with some kind of voltage source which is similar to sine wave, and this is very useful. These resonant inverters are very widely used, especially in the inductor cooker that we use. The inductor cooktops are generally working on resonant inverter technology. Now, there is one disadvantage to this resonant inverter. The disadvantage to this resonant inverter is that when, for example, when the switch T1 was turned on, the capacitor got fully charged and stopped and opened the circuit, and T1 got turned off automatically. At that time, T2 was not turned on, and as a result, there is a very high voltage across T2, which may damage the switch T2. As a result, there is a risk of switch damaging in half-bridge resonant inverters. The issues or the problems with the half-bridge resonant inverter that switch might get damaged is solved in the full-bridge resonant inverter by using the concept of bidirectional switches. So the switches are there, and the switches are in bridge configuration, as we have always seen, full bridge configuration as we have already seen, and we have the 4 diodes which are acting as a protection parallel to the switches in the opposite direction. Then what happens when switches T1 and T2 are turned on? Current flows in this direction. It at first charges the inductor, say T1 is turned on. So what happened, it at first charges the inductor, then the inductor gets discharged and it gradually charges the capacitor. When the capacitor gets fully charged, no current can flow in this direction again, and as a result current in this direction becomes zero. Now the capacitor is charged with plus at this end and minus at this end, and capacitor wants to get discharged. In half bridge inverter, capacitor couldn't get discharged unless the other switch was turned on. But in this case, as long as T3 and T4 are not turned on, and in that period of time, it will get discharged through D1 to the voltage source and come back through D2. As a result, even when no switch is turned on, the capacitor is getting a path to get discharged. As a result, there will be a voltage in negative direction, and once we turn on the switch 3 and 4, we again will find negative voltage. That is, at this stage we are turning on, at this stage we are turning T1, T2, and at this stage we are turning T3, T4. And at this interim stage that we have, in this stage diodes are conducting. Since diodes are conducting, the voltage across the diode are 0.7 volts, that is very low, and as a result at no point of time very high voltage is created across any individual switch, and since very high voltage is not created across the switch, there is no possibility of a switch getting burned. So we can see that the full bridge resonant inverter gives a better wave shape, or closer to sinusoid wave shape as compared to the half bridge resonant inverter, and switches are also protected in full bridge resonant inverter. As a result, full bridge resonant inverter is actually a better configuration than a half bridge resonant inverter. That's all for this small lecture on resonant inverters. In the next lecture, we'll be learning about multi-level inverters.